Hello, welcome to our presentation on quantum dots in noise-resistant quantum key distribution systems, and my name is Leah.
My name is Prahlad Sarvanapriyan.
My name is Nidhi Prasad.
My name is Stephen Benny.
I'm Shantwell.
I'm Ishan Savasabuni.
I'm Achintya Paningapali. So, as an introduction, you might be wondering, what are quantum dots? Quantum dots are small nanoscale particles from 2 to 10 nanometers. They have unique optical and electronic properties, and they're made of numerous materials. However, they have similar properties. They all function similar to transistors in electronics. However, they have a single electron spin with up or down, similar to a qubit.
What is a QKD? A QKD stands for a quantum key distribution system, and it basically is a secure communication method that uses quantum mechanics. Specifically, it uses quantum entanglement and superposition of qubits to ensure a safe transfer for later communication. It is also designed to be able to detect the presence of an eavesdropper. So in a regular open data channel, you won't really know if someone eavesdrops, but in QKD, an eavesdropper has to disturb wavelengths, which can be easily detected by Alice and Bob, the two correspondents. And QKD has a lot of applications, including secure communication, financial services, government and defense, healthcare and medical research, critical infrastructure protection, and quantum internet.
So what are some limitations of current QKD systems that we are trying to solve? Most current real-life QKD systems employ single photon emitting pulse laser diodes to send photons and photodiode detectors to detect photons. However, a limitation of using these hardwares is that they are very sensitive to outside environmental factors such as temperature and background radiation, all of which can cause the quantum states which are emitted to be less reliable to measure. Additionally, even expensive current technologies still have limitations in accuracy of emitted wavelength. QKD is meant to be done in the outdoors over large distances, so these environmental noise factors will inevitably play a big role. Factors will all make QKD less secure. Quantum dots presents an alternative to using these limited current hardware. Quantum dots, similar to laser diodes and photodiode detectors, can both transmit light and detect light, as well as enter superposition and entanglement. And what makes quantum dots an interesting alternative that not be used to noise. This is because quantum dots can be engineered to emit single photons with extremely high wavelength precision. Additionally, quantum dots can operate just fine in room temperature conditions, eliminating any worries for temperature-related noise. And finally, quantum dots can be controlled to have very narrow timing jitters, meaning that we can accurately control when a quantum dot emits photons.
So the goal of the project is to simulate and investigate the impact of quantum dots on enhancing the security and reliability of QKD systems. We have three models. We have the QKD model, the quantum key distribution model, the quantum dot model, and the noise model, which mainly models spin and charge noise.
The first step to our project was to implement the standard quantum key distribution model with code using the IBM Qiskit Python library. We modeled individual photons sent between the two parties as standard qubits, and we were able to model photon superposition and entanglement using the Hadamard and C0 quantum gates. To ensure that our basic quantum key distribution scheme functions, we simulated the scheme with and without the presence of an eavesdropper, which QKD is designed to detect. We were able to successfully determine the presence of an eavesdropper during the simulation, which confirms that our simulation is valid. Later, we will combine this base QKD model with other models. We plan to incorporate our noise model to analyze the effect of noise on the quantum dot QKD system.
Let's now talk about the QD model. Using a function we named variational form, we constructed a quantum circuit representing two quantum dots in the quantum key distribution system. This circuit, using rotation gates and parameterized by params, allows us to explore different configurations. The chosen number of qubits corresponds to the quantum dots in our simulated QKD scenario. Envision the quantum circuit as a structured environment governed by rotation gates, and in the parameters are denoted as params. These parameters introduce a dynamic element into the circuit, enabling the amalgamation of various configurations for our quantum dots. Moreover, this explicitly specified number of qubits in this quantum circuit aligns precisely with the quantum dots in our QKD scenario. This quantum circuit, meticulously directed by the variational form function, serves as a computational canvas for crafting the quantum representation of our simulated quantum dots. At each instance of a rotation gate and adjustment of parameters, we unveil a multitude of configurations, akin to a meticulous exploration of the nuanced behavior of quantum dots within the QKD system. This systematic construction not only mirrors the behavior of quantum dots, but also operates as a controlled computational environment. It facilitates a profound analysis of the impacts of different configurations on the QKD system, devoid of informal analogies. The quantum circuit becomes a structured platform for dissecting and comprehending the intricacies of quantum dot dynamics within the context of quantum communication. Moving on, there is a polydict dictionary which holds poly operators, and it acts as observables for quantum dot interactions in the QKD system. These operators define the characteristics of quantum dots. The Hamiltonian, a summed op of polysum op instances, provides a mathematical expression encapsulating the quantum dot system's features. These operators, in simple terms, are like detectives. They observe and record different aspects of how quantum dots behave. Spin, orientation, and other quantum features are their specialties. The polydict we use essentially compiles these observations, giving us a manual to interpret what the behavior of the quantum dot is. Now onto the Hamiltonian, which is just a sum of poly operators. Imagine it as an equation that sums up all of the characteristics we extracted from the polydict. This equation becomes a roadmap, a mathematical representation of the quantum dot system's features. This isn't abstract math for the sake of it. The Hamiltonian is the key to understanding the impact of different quantum dot setups on the stability and reliability of the QKD system. It's the bridge between the observations we made with the poly operators and the practical implications for a quantum communication system. So in essence, the polydict and the Hamiltonian are like our toolkit. One helps us observe and the other helps us analyze. It's just a straightforward approach to uncovering the intricacies of quantum dots and how it influences the robustness of the QKD system.
Okay, to add on the QD model, now let's see how quantum dots behave with the quantum key distribution QKD system. Our tool of choice for this exploration is the variational quantum eigensolver, the VQE algorithm. Think of VQE as a precise investigator on a mission to unveil the ground state energy of our quantum system, kind of a sort of cosmic detective probing the stability of quantum dots within the QKD setup. The method involves adjusting variational parameters, essentially tweaking the conditions to simulate different scenarios. It's similar to orchestrating controlled experiments to observe how quantum dots respond within the QKD framework. As we manipulate these variational parameters, VQE takes charge, meticulously navigating through the quantum landscape to pinpoint the optimal conditions. So what does it bring back? A set of optimal parameters in the ground state energy. So these optimal parameters are not just any value, They encapsulate the specific rotations and maneuvers that guide our quantum dots into stable configurations within the QKD system. It's related to decoding the language of quantum dots to understand the precise combination that ensures the stability of the system. The ground state energy in this context, as it acts as a weather glass for stability. A lower energy level signifies a more stable arrangement of the quantum dots, indicating resilience against external disturbances. It's a quantitative measure of how well our quantum dots maintain composure within the QKD system. The outcomes, the optimal parameters and the ground state energy, are more than numerical results. They are the keys to unraveling the intricate behavior of quantum dots within the tailored context of QKD. This methodical investigation provides valuable insights, paving the way for the strategic engineering of quantum dots to enhance the security and of quantum communication systems. So you might be thinking, why does this matter? So as stated before, the optimal parameters we get from the VQE guide the actions of the quantum dots. These parameters, represented as rotations and manipulations of the quantum circuit, set up stable arrangements. Watching how these parameters change gives us insights into preferred states and configurations that make the QKD system more stable and resilient. Tracking the evolution of optimal parameters over time shows us how quantum dots interact, revealing patterns that contribute to system stability. This understanding helps us map out quantum dot behavior and develop strategies for optimization. Ground state energy is like our stability gauge. Lower energy means a more stable quantum dot set up in the QKD system. This stability translates to better resistance against external disturbances, boosting the overall reliability of the system. When we analyze variations in ground state energy, we get a sense of how well quantum dots can handle changes in their environment or system parameters. Quantum dots with lower ground state energies emerge as the sturdy elements, making the QKD system robust. Optimizing quantum dot performance becomes easier when we understand variations in ground state energy. Targeting configurations associated with lower energy states improves the reliability and security of the QKD system. So, in a nutshell, diving into the results with a detailed analysis, considering different parameters, it helps us grasp how quantum dots play a vital role in securing and making the QKD system reliable. So that's all in the QD model.
So the purpose of a noise model is to explore sources of noise, such as charge noise, environmental noise, background radiation, etc., in order to identify how they affect QKD systems. But for the purpose of our research, we use the Qiskit Air library to create a model that explores spin and charge noise. And with our noise model, we also aim to figure out potential strategies to mitigate these noises. So spin noise is a series of fluctuations in the spin degrees of freedom of electrons in a quantum dot. And this basically means that there are random fluctuations in the spin orientation of electrons in a quantum dot. And within the context of quantum computing, quantum dots are used as potential qubits. And so these fluctuations can affect the reliability of quantum operations. Spin noise is represented through a Pauli error, and Pauli errors are common errors in quantum computing that can arise from various sources, such as imperfect gates, environmental interactions, or other noise mechanisms, and the error rate is dependent on temperature.
In our noise model, we also represent charge noise. Charge noise is fluctuation in the amount of electrons in a quantum dot. These fluctuations often cause errors in quantum operations. In our noise model, the charge noise is represented through a stochastic matrix. We calculate the error rate or amount of error based on the standard deviation of the charge from the mean. We also represent the effect of a magnetic field on the quantum dot in our model. We represent the effect of the magnetic field with a Hamiltonian. A Hamiltonian is a mathematical operator that represents the total energy of a physical system. Our Hamiltonian is time-dependent, and it is based on the cosine function to represent oscillations in energy. So we will be implementing our noise model on top of both our quantum key distribution system and our quantum dots. Now our goals and future work is to figure out how to integrate all three models and then generate the results. Based on the integration system, we'll be able to analyze the effects and advantages of parameters such as quantum dot size and error correction codes within the model. Based on our modeling, we aim to design new quantum key distribution systems that are noise resistant for the most secure and accurate systems with long distance capabilities that can be applied in a real world scenario. These are our citations. And thank you to ASDRP and Dr. McMahon. If anyone has any questions, you can ask them now.
Can you go back to the citation slide? Let that one stay up for a minute while you are. All right, anybody have any questions?
I have a quick question. It was a good presentation, but say like for AI, like do we use computers? What is the device used for this quantum dots?
So despite quantum in the name, we're actually not using quantum computers here. The actual control system of QKD can be controlled with a classical computer. The reason why there's quantum in quantum key distribution is that the photons use superposition and quantum entanglement in order to have the quality of when an eavesdropper detects it, the superposition will collapse. So basically there's going to be data lost. And then the other party can easily detect that and know that there's an eavesdropper. There's no actual quantum computers involved.
Okay, thank you. So basically, this is a hypothetical, or it can be implemented in practice, whatever the
Oh
research.
yeah, so this is actually a really new technology. This has been implemented, I think, within the last decade. For example, China actually launched a satellite that did successfully implement quantum key distribution.
All right. Yeah, thank you very much.
Yeah, I actually also have a question. To represent quantum dots, what program or like sort of like platform do you use to represent and like analyze quantum dots?
All of our code is written in Qiskit, which is a Python library through IBM. So we are writing this all in Python using IBM's platforms, as they are one of the leaders in quantum computing currently.
Oh, so it's just Python and like the library from IBM?
Yes, as within IBM, there are opportunities to either run a simulator, what quantum, which is what Qiskit Air is, as well as run your operations on real quantum computers, which only have around 5 to 20 qubits.
Oh, okay.
Okay, if there are no other questions, thank you folks for an excellent presentation. I will go ahead and turn it over to the next presenter. Next.